Our next speaker is Jeanne Crassous. She's a research director at the CNRS, something similar to the CSIC here in Spain. And she's working at the University of Rennes in France. She is a specialist also in on our organometallic systems, organometallic molecular materials, and mainly also on chirality. And she's going to talk about Helicenes. Is that correct? Okay.
That's correct.
The floor is yours, please.
Thank you. So thank you very much, Enrique. It's a great pleasure to be here in this in the middle of this fascinating program, scientific program, and I'm very grateful to Eugenio to invited me for this nice event and to be in front of all these students. Actually, the story started in 2019 when Reiko, who is here also, invited both of us in an event in Japan, in Kumamoto. So she organized a meeting with Professor Ihara. And so Eugenio found that it was a friendly and very friendly and highly high-level scientific atmosphere, and decided to invite us, both of us, to be here in this event. So because of the COVID, it took more time, but I want to warmly thank Eugenio for this kind invitation. So probably I will provide different knowledge compared to what you are used to, because I'm an expert in chirality. So I'm sure you know what is a chiral molecule. It's a molecule which can exist into two forms that are not superimposable through a mirror. And you know that there are a lot of important chiral molecule, and homochirality is an important property of life. So like in sugar and in amino acid, and that some of the chiral molecules have important properties, biological properties. You have different types of chirality in chemistry. You can have a classical point chirality, axial chirality, planar, and so on. And in our case, we are focused on this helical chirality. So we deal with helicenes. So why helicenes? Because they are formed of orthofused aromatic rings. So when you have more than 5 or 6 aromatic rings that are fused together, you can have a helical topology, and these molecules are stable. Their configuration is stable. You can have a right-handed helix, which we call P, and a left-handed helix, which is called M. So these are 2 enantiomers. And because of this particular helical topology and extended pi conjugation in this molecule, they exhibit very strong chiroptical properties, and I will explain you what they are. So the most common chiroptical property, probably you know, is optical rotation. So you know that classical molecule, chiral molecule like sugar or maltol, they deviate the plane of light, polarized light. And you see they have some typical value, 50, around 50 for this type of molecule. For a helicene, because of the typical helical topology, is huge. You see, it's several thousand. So this is the first specific property of helicenes. Another chiroptical properties, which is very important, is what we call the secular dichroism. So it's like the UV spectroscopy, but with dealing with secularly polarized light. So secular dichroism is a difference between the absorption coefficient of left-handed secularly polarized light and right-handed secularly polarized light. So when the chiral molecule absorbs more of one compared to the other one, you have either positive or negative signal. And what we define is a dissymmetry factor, which is a ratio between the circular dichroism and the UV spectrum. So it's this delta epsilon over epsilon, which has this expression. Another chiroptical activity, which is growing nowadays, is a circularly polarized luminescence. So it's kind of analog property of compared to circular dichroism, but in emission. So a molecule which is chiral and which emit light will emit more circularly right-handed circularly polarized light compared to left-handed circularly polarized light. So the emitted light will be polarized. Maximum, so we usually define the dissymmetry factor, which is the ratio between the difference and the sum, and the half sum. And the maximum value are +2 or -2 for the pure right-handed or left-handed emitting light. But classically, for normal chiral organic molecule, it's quite small. It's around 10 to the -4 or 10 to the -3. So why is it important to look at this circularly polarized emitting light? Because actually in everyday life, we use it. For example, when you go to the cinema, you go to look at the 3D movies, you use these glasses that have a circular polarizer, and your mind will reconstruct the whole image from a right and left-handed image. And we think that it's important also in optoelectronics and in OLED technology, because when you have your smartphone, actually it has because you have to remove all you have anti-glare system, because otherwise, like sunglasses, the light is reflected, and so you usually use a polarizer. So in your smartphone, you have polarizer, and you have a quarter wave plates that transform the linear polarized light to circularly polarized light. So there is a technology inside your mobile phone. But when you use this technology, actually you lose half of the light due to reflection phenomena that cut half of the light. So we think that if we use an enantiopic chiral molecule which will emit an enantiopic light, you will recover this 50% that is left, because you don't block anymore the light. So there is really an interest in a technological interest in using chiral circularly polarized light in OLED technology. So going back to the Helicene molecule, as I told you, they absorb strongly the light, and this can be seen by the circular dichroism, which strong value, delta epsilon value up to 300 is strong. But they also emit light. You can see that they are fluorescent. So the carbo-6 helicene is fluorescent, but you see the quantum yield is low, 5%. And the dissymmetry factor, the G-room, is around 10 to the -3. So what we need is to increase this value. So to make some, I'm a synthetic chemist, I make some molecular engineering to tune the molecule and to try to increase these values. So what we do is we use the chemistry of Helicene. We combine with coordination chemistry with metal, or with some special chromophores or dyes, and we see how these properties will change, will be increased, will be tuned. So by this way, we make some structural diversity. We try to find a new molecule, to prepare a new type of molecule, but also we want to have strong absorbers and strong CPL emitters. And because here we deal with magnetism, and we have heard a lot during the beautiful presentation from Roberta about spins. So I will try to show you a few examples combining chirality and spin magnetism also. So just one slide about synthetic synthesis. So how do we prepare this type of helicene? We use a typical reaction, which is used in Helicene chemistry, which is photocyclization. So it uses light to make this electrocyclization of this olefin, which is very simply prepared via a biovitic reaction. And we can install a great diversity of functional groups. So here I took the example of a triple bond. So we can put one triple bond or two triple bond. And then we can install on this triple bond a diversity of different groups, as I will show you. I want to mention here that I have a very nice collaboration with Professor Nazario Martin, who has used this compound to prepare beautiful helical bilayer nanographene. So this compound can be separated into pure enantiomers, because when you prepare the molecule, it's racemic, so 50-50 of the right-handed and left-handed. And we use what we call HPLC, chiral HPLC separation chromatography to separate the two enantiomers, right-handed and left-handed, and then we can deal with chirality. So this is the first illustrative example. So we decorate a helicene with a dye. So this is a pyrrolopyrrole. So we can introduce one or two diketopyrrolopyrrole, or we can also form small oligomers. And by doing this, so the diketopyrrolopyrrole is a dye that is used in the Ferrari cars. So beautiful red cars. So here is more like pink. And so it gives a strong absorption in the red region. And you still have this strong absorption coming from the helicene. So we have two parts in the UVV's spectroscopy. And if you go to the circular dichroism, you have actually the typical signature coming from the helicene itself, which gives you the positive negative band, which is really typical of the right-handed helicene. But on top of that, you have a new signature coming from the presence of this diketopyrrolopyrrole. So, and this response is very strong, because what is surprising is that the diketopyrrolopyrrole is not a chiral unit, it's planar, but it's present in the helical environment of the helicene. And because of that, it will see the chirality of the environment. And if you zoom in this part, you can see that there is a positive and negative band. And this is typical of what we call exciton coupling chirality. So when two chromophores with strong electric dipolar moment are placed in the chiral environment, they will interact with each other and give you this typical signature with a positive and negative couplet. And we have found that you have this phenomenon in helicene chemistry. And as a result of this, you have not only a strong absorption in helicene chemistry, but these molecules are also emitting. And you have luminescence, classical fluorescence, and you have circularly polarized emission, which is quite strong. And we see that it's bigger when you have two chromophores, because they interact through space through this exciton coupling. It's bigger when compared to when you have only one chromophore. So it's a really convenient way to improve the chiroptical activity of the chiral molecule. Another nice example, illustrative example, is the combination of helicene with this electron accepting naphthalimide system. So you have a kind of a donor-acceptor molecule. And so acceptor, donor, acceptor is like a pseudo-quadrupolar structure when you have two chromophores. And when you have only one chromophore, it's like a dipolar molecule. So this molecule, because they are polar, they show nice solvatochromism. It means that they emit the light, which will be different depending on the polarity of the solvent. So you see a nice redshift when you increase the polarity of the solvent. And this gave us the opportunity to look at how the CPL signal is changing with the polarity of the solvent. This was not observed before. And we could see that when we use a less polar solvent like cyclohexane, we have a strong response. And when we go to more polar solvent like DMF, we decrease the CPL activity. So we go from a pseudo quadrupolar structure to a dipolar structure due to the influence of the solvent itself. This molecule, so I've shown you that they have a nice CPL response, which can goes up to 10 to the minus 2. It's only 1%, but for an organic molecule, it's quite high. And we have been able to introduce, first of all, we wanted to understand why it's so high. And actually, if you look at the expression, a simple expression of what is a UV, is the UV band is a square of the electric transition dipole moment. And by analogy, the CD is a scalar product of this electric, but also the magnetic dipolar moment. So when you look at the intensity of the CD, you look at the product of mu and m multiplied by the angle of the two vectors. So this angle is very important. If the two vectors are collinear, is the perfect situation where you have strong response. So that's why in this helical helicene, you have a strong CPL activity. It comes from the good orientation of the transition moment. Oops, sorry, I think I made a mistake. Okay. Okay, so because we had a nice chiral molecules with a nice CPL response, we wanted to see if it was possible to incorporate them into an OLED and make an OLED which emits light, but circularly polarized light. And indeed, it's possible. We are not the first one to do that, but we have collaborated with people from the CEA in Grenoble, and they have a special technology to prepare some top emission OLED. And if you see the light that is emitting through the OLED, it's a circularly polarized light. So you have more right-handed or more left-handed light, depending on the enantiomer you use. So let's now go to another aspect. In this organic helicene, still with this triple bond that enable us to introduce some aggregating units. So we do this in collaboration with Luis Sanchez. Some of you know him very well. So I was very pleased to collaborate with him. So he's an expert in this type of units, which can which enables to install some hydrogen bonds. And because of this, so you see here, you have the helicene, which is substituted in two different positions. And depending on this position, we have different organization. So when you look at the aggregation going from a good solvent to a bad solvent, when you go to the bad solvent, you generate this aggregate. And through by NMR, you can see how the substituents are close to each other. So in one case, you have a head-to-tail organization. In the other case, you have a head-to-head supramolecular organization. This can be seen by noisy NMR. And as a result, when you make this aggregation, you see and you follow the CD, you have a change in the CD response. So in one case, you can see in this case, you have the increase of the CD. And in the other case, when you have a head-to-head organization, you have a change in the CD, but some of the band are changing sign. And especially the low energy CD band are inverting the sign. You can see here the resulting CD response. And because it's a lower energy, so it involves the lower excited state, which is the one which is involved in the emission process. Then as a result, the CPL of this special organization is inverted its sign upon aggregation. So it's a rare example of CPL inversion. upon aggregation. And on top of that, because this compound self-assemble very well, they can self-assemble on the surface. So this was observed on HOPG by AFM. You can see that in this position, you form a kind of globular aggregate, while in the other situation, you can generate some fibers, and we can guess that there is a kind of helical fibers. And we have been discussing, and we have a collaboration with Ron Naman from Weizmann Institute, is a big expert of spin selectivity, chiral-induced spin selectivity. And we were thinking that maybe this supramolecular aggregate, which are chiral, would be appropriate to observe this type of phenomenon. And this was so this is what we call chirality-induced spin selectivity, is when you have a surface. For example, you put a chiral molecule like DNA, and you have some experiment that can help you to see how the electron is transformed. The spin, the electron spin is transported through the helical layer. And there is a selectivity, which means that the spin will be selected either up or down, depending on the helicity of the molecule. So to a simple explanation that can be used is centripetal force that is induced when an electron goes through the helix, when it moves through a helix. And upon a magnetic field, you can have either up or down, and the energy between both is different. So this can may enable to generate some spintronic devices that could function at room temperature, because chirality can help to organize the spin, and so to generate some magnetic effect without the help of any magnetic field. So it's a very fascinating domain, which is growing very fast now. And we have been pleased to finally find a good system which works in this case. So this supramolecular aggregate. So this, we could see it by magnetic conductive IFM, which is a typical experiment which works well for this type of measurement. So you have a magnet, you have a surface formed of typically nickel and gold. Nickel for the spin, generating the spin. Gold is a metallic surface, and it will enable you to organize a chiral molecule on the surface. And when you apply a voltage and you measure the current which goes through, depending on the chirality of the system, it will either make the current pass or not. And depending also of the direction of the magnetic field, in one direction, there is the spin can go through. If you invert the direction of the spin, it will not go through. So this is why we call it spin selectivity. And what was nice in this case is that it's very strong effect. So if you define the electron spin polarization, which is the difference between this current, which is up, and this current of the magnetic down, you see, you can have an idea of the general effect, and it's very strong. It's around 80%. So you have almost, the spin is transferred very efficiently, or is blocked when you invert the chirality. So going back to the circularly polarized emitting system, we develop also organometallic chemistry. So we introduce a metallic ion into a helical backbone, and by this way we can take advantage of the chirality of the helicene and the properties of the metal. So for example, if you choose this platinum into phenylpyridine type ligand, you have you can take advantage of the phosphorescence properties of this metal. And at the same time, you have the nice chiroptical properties coming from this helically shaped molecule. You can see this very nicely by a theoretical calculation. For example, here you have the HOMO and LUMO, and you see that the platinum is fully conjugated with the orbitals of the pi ligand. So as I told you, you take advantage of the chirality of the ligand and the properties of the platinum. Here it's a red phosphorescent emitters. And because of its chiral, you also have circularly polarized phosphorescence. So at that time, it was the first example of helical helicene being phosphorescent at room temperature. And some years after, the group of Fuchter and Campbell at Imperial College, since the synthesis is quite simple, they were able to reproduce it, and they incorporated it in an OLED, in a simple OLED, and they have found that the G lume, so the dissymmetry factor, which is around 10 to the minus 3, 10 to the minus 2 in the molecule, was strongly enhanced into the device. So it goes to 0.2 or 0.4 in the device. So there is an effect, inherent effect of the structure of the OLED itself, which introduce an increase. And we are trying to understand through a European project, so Hel for ChirOLED. Altogether, we're trying to understand what are the factors and the parameters that influence this effect. So I'm a synthetic chemist, so I like to introduce new ligand, new type of ligands and new metals. So for example, there is this NHC chemistry, which is developing very fast. And in our case, we have shown that it's possible to develop helical NHCs. And we have introduced heavy metals like rhenium. And because the rhenium is a heavy metal, it enables to generate some phosphorescence. But here you deal with two types of chirality. You have the chirality of the helicene, so a helical chirality, but the rhenium also is a chiral center. It has an octahedral environment. You can define two stereogenic forms, so two enantiomeric forms that you describe as anticlockwise and clockwise. So which means that you deal with diastereoisomers, and playing with the stereochemistry of the rhenium, you can increase or even invert the CPL signal. So you have a kind of mismatch effect that you can observe clearly in the CPL response. And what was nice also in this example is that we could see the effect of the stereoisomer, so the stereochemistry of each isomer on the photophysics. So if you change the rhenium from clockwise to anticlockwise, you change the quantum yield and you change the lifetime. And if you go from the chlorine to the iodine, also you drastically change the photophysics. And we interpret this as because when the chlorine is close to the helicene, is a kind of protected from the environment. When it's from the other side, is far away from the helicene ligand, and it's more prone to interact with the solvent, and then the photophysics would change. So this example shows how subtle our modification to understand what are the parameters which influence the photophysics. So a last example that I wanted to show you how the magnetism is interesting here. We have introduced the chemistry of pyridine. You know, pyridine is a very rich ligand in coordination chemistry. So we have developed the chemistry of helicene pyridine and incorporated into a lanthanide chemistry. So if you use this ytterbium, you can have this molecule complex with one pyridine helicene and 3 HVAC ligand. And this is X-ray structure. And you can crystallize into a nice crystal that you can study. And this gives the opportunity to combine chirality and magnetism through what we call magneto-chiral dichroism. So magneto-chiral dichroism doesn't use right-handed and left-handed light. It just use magnetic field combined with a non-polarized light. So when you combine two collinear light represented by this K vector and with a magnetic field, you have this new component in the absorption, which is called the magneto-chiral dichroism. So it comes in addition to the absorption, the classical natural CD, the magnetic CD, which is the Faraday effect, and then there is a cross effect, which gives you this new phenomenon that was mainly developed experimentally by Gert Ricken and in combination with Cyril Train and Matteo Azzori. All together, they make a nice, they have a nice apparatus in Grenoble. And now we can share different compounds and we can discover new things in this domain. And here you see you have a dichroic signal, and you can define similarly to the CPL and the CD the dissymmetry factor corresponding to the magnetochirality. And in the domain of lanthanide complexes, actually Gert Ricken with Raupart in the 1997 he addressed this phenomenon through the emission of lanthanide. You know, lanthanides are nice emitters, so it could demonstrate the presence of magnetochirality in emission. In our case, we have shown that it's also possible to observe it in absorption. So here are the typical line of the ytterbium in absorption, so in the red infrared domain. And they were able to show very nicely to observe magnetochiral dichroism of our Helicenes ytterbium complex with a nice influence of the temperature. You see the signal is growing strongly when you lower the temperature, and is growing also strongly when you increase the magnetic field. And you obtain the mirror image when you change the enantiomer or the direction of the magnetic field. And interestingly, I was delighted to see that thanks to this experimental result, they were able to identify some theoretical terms that were proposed by Baron and Bromwich in 1984. By comparison, I think with the Faraday effect, they were explaining theoretically what is this effect in terms of ABC term. And for the first time, because of this strong variation, it was possible to put a value on A and C, and to show that the A term actually is it's constant with temperature, and the C term is inversely proportional to the temperature. So you see how our chiral molecule help to understand and to look more carefully at the fundamental phenomena. So these are all the people I'm working with, so expert in magnetism, expert in magnetochirality, and this compound also are emitting circularly polarized light, but in the far infrared, so you need to have the special apparatus to look at it, and we do this with people in Lyon. So as you saw, it's a highly collaborative work, so with many people. I will not go through because it will take too much time, but I'm really grateful to all of them, and grateful to all the people who have been involved in this work. So our team, we share with other part of the group who are expert in phosphorus chemistry, so Pierre-Antoine Bouy and Muriel Isler. And in my case, I deal with this topic with Ludovic Fabreau, and these are all the students. And finally, I want to advertise a PhD funding we got from the European Commission. So it's a collaborative work, and we have to hire people from other countries. So I'm looking for somebody from a country different from France. So if you are interested, or if you know some friends please, you can apply. And so with this, just a small advert, if you want to know more about chirality with Reco and other people in Bordeaux, we are organizing this chirality meeting in next October in Biarritz, beautiful place to spend time. Thank you very much.
We have only time for one short question because the lunch has been advanced to 1.5. Then we have less time. Please, any questions from the students? Any questions from the audience?
Maybe we can discuss during lunchtime, but I'm wondering if you are observing chiral luminescence. So you send unpolarized light, it becomes circularly polarized. And then you add a magnetic field. The Magneto-chiral dichroism cannot result from this combination, so that at the end, the light that is traveling along inside your material becomes circularly polarized.
So you want to combine circular dichroism?
No, I'm wondering if it can be an additional effect that you see magneto-chiral dichroism.
I think so. I think in the CPL of the last example, for example, when you lower the temperature, you have magnetic effect that will appear, and you have a combination of everything.
Okay, well, maybe we can.
And within this project, we would like to look at it, but it's not that easy. But I think it's a good opportunity to see how the magnetism is involved in the CPL.
Okay, thank you.
This is
okay. Let me thank again, Jeanne.